All right, so today we are going to be discussing the operational amplifier. We are going to get a very high level overview of how circuits containing op amps work. We are not going to get into the nitty-gritty details of op amps themselves. And the reason for this is because op amps are a pretty advanced circuit. What I'm about to open up here is a data sheet for an op amp that I teach in my Circuits 2 class. Let's see if I can find it really quickly. And this picture that I'm showing you right here, let me zoom out so we can see all of it, is a functional block diagram for an op amp. Now this is well beyond the scope of our class, but this particular circuit contains 22 bipolar junction transistors, 11 resistors, a diode, and a capacitor. It is a multi-stage amplifier that consists of a differential pair as its input stage, a Widlar transistor current source as a biasing network, and then it contains a push-pull amplifier network at the output, which allows its output voltage to swing between VCC plus and VCC minus. I understand that overwhelmingly what I just said is a lot of gibberish to you all, okay? What's absolutely wonderful about op amps is that for the most part, they obey a couple of pretty straightforward rules. And if we know those rules, we can analyze circuits that contain them without having to understand what all of these transistors, resistors, diodes, and capacitors are doing. So, sorry, that's the wrong set of notes. So for us here in Circuits 1, we're going to represent an op amp using the following symbol. So a triangle is the generic symbol for an amplifier. Our op amp contains two input signals. One of them is denoted by a positive sign, and the other is denoted by a negative sign. The terminal that's attached to the positive sign is what's called the non-inverting input terminal, and the terminal that's denoted by the minus sign is the inverting input terminal. We'll talk about more about what non-inverting and inverting means here in a little bit. On the right-hand side, we have our output terminal. So effectively, we can apply two input voltages and get one output voltage in this circuit. There are also a few other terminals which, for the sake of our analysis, are going to be considered optional. But for the sake of practically realizing an op amp circuit, like if we were having this class with live lectures and actually doing the labs, you would be required to build an op-amp circuit. And op-amps are what we call active devices, which means they require external power to work. And so two other terminals that we would have to pay attention to are the VCC plus and VCC minus terminals, which are used to apply the positive and negative power supply voltages. This quantity VCC plus, whatever positive power supply voltage we apply, and the quantity VCC minus, which is whatever negative power supply voltage we apply, are what limits the output voltage of the device. So the output voltage of an op-amp will always fall between VCC plus and VCC minus, okay? All right, so now I'm going to introduce our two op-amp rules, okay? I'm going to introduce these without a lot of explanation, largely because it's beyond the scope of this class. The first of which is that no current may flow into or out of the input terminals of an ideal op-amp, which is what we're going to be dealing with. And so what that means is that this current, which I'm going to label I superscript plus, has to be 0 amps always. And similarly, this current, which I'm going to label I superscript minus, must also be 0 amps. Our second rule for how op-amps behave is that there can be no voltage difference between the input terminals of an ideal op-amp. So let's call this voltage associated with a non-inverting input terminal V superscript plus, and this voltage associated with the inverting input terminal V superscript minus. Op-amp rule number 2 says that there is no difference between these voltages, which implies V plus, the voltage present at the non-inverting input terminal of our op-amp, must be exactly equal to V minus, the voltage present at our inverting input terminal of our op-amp, and vice versa. Okay. All right, so let's see what's going on in the chat. Thank you. All right, so we are now going to get into analyzing some op-amp circuits using these two rules, and then just our circuit analysis techniques that we have developed to this point. Okay. So let's start by analyzing the following circuit. Here we have our op amp. I'm going to flip things over here. I'm going to put the inverting input terminal on top, and the non-inverting input terminal on bottom. And here is my output. And now we're going to make some connections. Okay. So one thing that I can do is connect my non-inverting input terminal to ground. I'm going to place a 5 kilo ohm resistor between my inverting input terminal and my output terminal. And I'm going to put a 2 milliamp current source here between my inverting input terminal and ground. And what our goal is for this circuit is to determine the quantity V out. For a circuit like this, and honestly for the overwhelming majority of op-amp circuits you're going to see in this class, in fact, I can think of only 1 or 2 that I might give you, we can actually follow a pretty simple 3-step process in order to determine our output voltage, which will always be our quantity of interest. Okay. So our first step is going to be apply rule number 1 and determine the voltage V plus, which is the voltage present at the non-inverting input terminal. So if I apply op-amp rule number 1, this is me noting this current has to be 0 amps, and this current has to be 0 amps. Now I'm going to determine the voltage V plus. By inspection, V plus in this case is 0 volts because our non-inverting input terminal is connected directly to ground. Step number 2 is to apply rule number 2 and perform Kirchhoff's current law at the inverting input node. So if this voltage V plus is 0 volts, op-amp rule number 2 says that this voltage V minus must also be 0 volts. If we apply Kirchhoff's current law at the inverting input node, and I'm going to write KCL where the current flowing in is equal to the current flowing out. So just to be clear here, I'm saying that this current flowing into the node has to equal this current flowing out of the node. what we will get is 2 milliamps is equal to 0 volts minus whatever our output voltage is divided by 5 kiloohms. Step number 3 is simply solve our KCL equation for V out. So with a little bit of algebraic manipulation here, we should be able to see that V out is negative 2 milliamps times 5 kiloohms. And this gives us a value of negative 10 volts. So we've analyzed our first op-amp circuit, okay? Following this simple 3-step process will get you the result you're looking for in the overwhelming majority of the circuits that we will analyze. And the next circuit we're going to analyze is one of the few where it won't work, and I'll tell you how to treat those as well, okay? Before we do that though, I want you guys to notice something here. And this is a key indicator of how op-amps behave. So this is going to help you know whether or not you're at least in the ballpark of a correct answer. We had a positive input signal, meaning the current was flowing into our op-amp, but our input signal was applied at the inverting input terminal. So a positive signal in to the inverting input terminal gave us a negative output voltage. That's what the inverting input terminal does. It changes the polarity or inverts the polarity of the input signal, okay? If we had a circuit where we applied a voltage at the non-inverting input terminal, we'll cover one of those in just a moment, we'll see that our output signal will be a positive voltage. So the inverting input terminal flips the sign on the output, the non-inverting input terminal keeps the sign. All right. Let's look at a second example problem. So we're going to start with our op-amp. This particular example, I'm going to draw the non-inverting input terminal on top, the inverting input terminal on bottom. Drawing my terminals here. All right, so what I'm going to do here is I'm going to put a voltage. Let's put positive polarity on the left, negative polarity on the right, like so. And let's let this be a 3.5 volt source. I'm going to apply a voltage directly to the non-inverting input voltage or input terminal. Let's make this a 6 volt source. And our goal here is to determine V out. Okay. So if we try to apply our three-step process here, things will be okay. Step number one, apply rule number one and determine V plus. So for rule number one, we know that this current has to be 0 amps. And this current has to be 0 amps. By inspection then, this voltage V plus must be 6 volts. Step number two is to apply rule number two. And perform KCL at the inverting input node. So if we apply rule number two, we would find that this voltage V minus must also be 6 volts. Now the problem with us performing KCL at our inverting input node here is that that would involve finding the current that's flowing through that voltage source, which we know from our development of the nodal analysis technique is problematic, okay? So if we ever have a voltage source in our feedback loop, which is this connection between our inverting input terminal and our output terminal, instead of applying KCL, we're going to perform KVL. And it's no longer going to be at the inverting input node because A, that doesn't make sense for a KVL. We need to identify a loop. So our loop needs to start at ground on the non-inverting input side and end at ground on the output side, okay? So you might be saying to yourself, well, Dr. Hartman, there isn't a ground on the output side. So let me fix that. And how I'm going to fix that is simply like this. Our voltage V out is a nodal voltage, meaning that it is measured with respect to ground. So that is the same thing as saying V out is simply the potential difference between our output terminal and ground, like so. Now I'm going to show you the loop that we'll use. So we'll start at ground here on the non-inverting input side. We'll jump across to our other input terminal through our voltage source to the output node, and then down to this ground. Okay. So another thing that I'm going to indicate here and we've already done it in a sense, is that the voltage drop across our input terminals has to be 0. That is what rule number 2 tells us. So if I write this KVL equation, what I'm going to have is -6 volts plus 0 volts plus 3.5 volts plus V out is equal to 0. And then rearranging this, we find that V out is equal to 6 volts minus 3.5 volts is equal to positive 2.5 volts. The only time, I get, sorry, step 3 should have been solved for V out. Let me write this here. Got slightly ahead of myself. The only time you'll ever have to use, I'll answer that question in just a moment, Devarier. The only time you will ever have to use this KVL method instead of the KCL method I outlined in the first example is if there is a voltage source that connects or that's placed between the inverting input node and the output node. If it's just a resistor or a wire or a capacitor, an inductor, really anything other than a voltage source, you can do KCL. But when there's a voltage source there, you need to do KVL. So Devarier asked the question, if starting at ground and ending at ground makes a KVL loop? And the answer is yes. So for Kirchhoff's voltage law, we are simply required to start and end at the same electrical potential. So starting and ending at ground is absolutely a loop. All right. Let's look at another example problem. So let's see, how am I going to choose to draw this one? Let's put the non-inverting input node on top, the inverting input node on bottom, like so. I'm going to connect the inverting input node and the output node with a resistor. Let's make this a 1 kilo ohm resistor. I'm going to have a 3 kilo ohm resistor here. And then on this side, draw this. Let's put a 2 kilo ohm resistor, kind of running out of room here, 4 kilo ohm resistor, and then a 10 volt source. Our goal here is to determine V out. So since this circuit doesn't have a voltage source connecting the inverting input terminal and the output terminal, we are going to do the three-step process involving Kirchhoff's current law. Okay. So step number one will be to apply rule one and determine V plus. So rule number one says this current has to be 0 amps. This current has to be 0 amps. And now we solve for V plus. Does anybody have any thoughts on how we might do that? All right, nobody's saying anything. So the first thing that I'm going to do is I'm going to identify V plus. So V plus is the voltage present at the non-inverting input node. Much like the output voltage, this is also a nodal voltage, which means that this voltage is measured with respect to ground. So in this case, V plus is the exact same thing as the voltage drop across this 2 kilo ohm resistor, since that's the difference between the non-inverting input node and the ground. Okay. Did me identifying that help anybody come up with an idea of how we might solve for that voltage? Voltage division. Wonderful suggestion, Devarier. So Devarier is absolutely correct. We can apply voltage division to this small network here on the left-hand side. I'm going to put a circle around it. In order to figure out what the voltage V plus is. So we can think of it effectively as finding the Thevenin voltage that's connected to, or the Thevenin equivalent voltage of the network there that I've circled, and then applying the Thevenin equivalent to that network. Another way that we can think about it that might be a little bit more straightforward of why voltage division is appropriate here is because any current that's leaving the positive polarity terminal of the 10-volt source has to flow through the 4 kilo ohm resistor. None of it can branch off and flow to the right through into the input terminal. So all of it has to flow down through the 2 kilo ohm resistor into ground, and then it comes back up through this ground. So effectively, we have a 10-volt source connected to two resistors that are appearing as if they are in series, and we just want the voltage drop over one of them. So applying voltage division, V plus is going to be 10 volts times 2 kilo ohms over 4 kilo ohms plus 2 kilo ohms. That's going to be 20 over 6, which is the same as 10/3 of a volt. All right. Step number 2. Is going to be apply rule number 2 and perform KCL at the inverting input node. So if we apply rule number 2, that tells us that this voltage right here, V minus, must be equal to V plus, which was 10/3 of a volt. Now we're going to apply KCL at this node, and I'm going to apply KCL by adding this current that's exiting the inverting input node and this current that's exiting the inverting input node together and setting them equal to 0. So the current flowing down through the 3 kilo ohm resistor is 10/3 of a volt divided by 3 kilo ohms. The current flowing to the right through the 1 kilo ohm resistor is 10/3 of a volt minus V out over the 1 kilo ohm resistor. We set this equal to 0. And then finally, we get to step number 3. Which is just solve for V out. So, going to do this algebraically here. 10/3 of a volt over 3 kilo ohms plus 10/3 of a volt over 1 kilo ohm is equal to V out over 1 kilo ohm. I've got that by simply breaking that fraction up into 2 parts and moving the V out term to the right-hand side of the equal sign. Now I'm going to find V out by simply multiplying everything by 1 kilo ohm. So V out will be 10/3 of a volt multiplied by 1 kilo ohm over 3 kilo ohms plus 10/3 of a volt multiplied by 1 kilo ohm over 1 kilo ohm. So that's 10/3 times 1/3, which is 10/9, plus 10/3 times 1. So that's going to be 40/9 of a volt. Now, obviously, if you wanted to, you could just take this equation, throw that into your numerical solver, and just solve for V out instead of doing the algebra. All right, I have one last example problem that I would like to work with you guys. And this is fairly representative of what I might put on an exam. And actually, this is representative of a difficult example that I might put on an exam. And we are going to be able to solve this using our 3-step process pretty straightforwardly. So this circuit is going to look like I've increased the level of difficulty by a large degree. But I promise you, our simple 3-step process will be all that we need to solve it. I'm going to put my inverting input node on top, non-inverting on bottom, like so. Here is my output. So let's start with the inverting side here. Let's put a 2 kilo ohm resistor right here. Here, let's have a 5-volt source in series with a 3 kilo ohm resistor. And down here, let's put a 1 milliamp current source. Down here, let's put a 4 kilo ohm resistor, excuse me. An 8 kilo ohm resistor. A 0.5 milliamp source. And our goal is to determine V out. So step number 1, we apply op amp rule number 1. This current is 0 amps. This current is 0 amps. And we find V plus, where V plus is the voltage here, which is the same as the voltage over the 4 kilo ohm resistor. Who can tell me how to find the voltage drop over the 4 kilo ohm resistor? Ohm's law. Absolutely right, Catherine. So what I believe Catherine is suggesting is that this 0.5 milliamp of current flows through the 8 kilo ohm resistor, and then all of it has to flow down through the 4 kilo ohm resistor before returning back in this loop. So using Ohm's law, V plus is simply 0.5 milliamps times 4 kilo ohms is equal to 2 volts. Now let's move along to step number 2. So step number 2, we apply op amp rule number 2, which means we find this voltage V minus. It has to be exactly equal to V plus, so it is 2 volts. And notice that that is this voltage for this whole node. Now we apply Kirchhoff's current law. And so I'm going to find KCL, or I'm going to apply KCL by taking this current, and this current, and adding them all together and setting them equal to 0. So let's start with the current flowing to the left through the 3 kilo ohm resistor. That's going to look like 2 volts minus 5 volts over 3 kilo ohms. Now we'll take the current flowing to the left through the current source. That's going to look like negative 1 milliamp. Now we'll take the current flowing to the right, which is the current flowing through the 2 kilo ohm resistor. So that's going to be plus 2 volts minus V out over 2 kilo ohms. Set this equal to 0. And now for step number 3, we simply solve that equation, right? So V out is going to equal 2 kilo ohms times let's see, 2 volts minus 5 volts looks like negative 3 volts over 3 kiloohms minus 1 milliamp plus 2 volts over 2 kiloohms. So negative 3 volts over 3 kiloohms looks like negative 1 milliamp. 2 volts over 2 kiloohms looks like positive 1 milliamp. So we have negative 1 minus 1 plus 1. So 2 kiloohms times negative 1 milliamps looks like negative 1. Sorry, 2 times a negative 1 is definitely negative 2. My apologies. And there we go. That is pretty much the hardest possible type of question I could ask you. Multiple sources, some of them applied at the inverting input terminal, some of them applied at the non-inverting input terminal, and our 3-step process gets us a result, okay? All right, so that is enough out of me for today. I want to make you all aware, and I'm going to send out an email here in just a few minutes. I will not be able to do a live lecture tomorrow as I have a meeting with some representatives from AEP SWEPCO and EPRI for a research opportunity for the electrical engineering department. And unfortunately, that meeting was set up to be at 2 p.m., which conflicts with our class. So instead of me giving you guys a live lecture, I'm going to just post a previously recorded lecture on the material, probably from this past spring's section of Circuits 1. The material that is going to be covered in that video lecture is commonly used op-amp topologies. So effectively, circuits involving op-amps that are used a lot in industry. If I'm being entirely honest, you can kind of treat this lecture as optional. It's not going to hurt anything if you don't view it, because really all that I'm going to be doing is using this 3-step process that we've developed to determine input-output relationships for op-amp circuits that are used a lot in practical applications. It's not going to hurt anything for you to watch it. In fact, it might give you more practice on seeing how I apply this 3-step process and all that kind of jazz. But this is honestly the one lecture where if you don't want to watch it, it's really not going to hurt much. So anyway, if you have any questions about anything, I would be happy to answer them. If not, have a great rest of your afternoon, and I will see you on Thursday.